Log on, tune in, find out. Another good idea from Cambridge.
So our second speaker is Justin Seabrook from Ricardo Consulting, and Justin has a PhD in the modelling of engineering emissions from UCL, and he's a technical specialist at Ricardo, responsible for tools and processes for engine development and testing.
Thank you very much, Dave. So my talk is about DoE in the automotive industry. It's not a series of case studies, it's more of an overview of the way that DoE is used in one phase of engine development. And then at the end, I've tried to suggest areas where hopefully the academic community can start to think about solutions that will allow us to continue to use DoE effectively in engine development. Okay, so I'll talk generally about how DoE is used. I'll talk about polynomial models because, like in most areas of DoE, polynomial models dominate, and look at some alternatives to those, some more sophisticated methods before talking about, if you like, the areas where engine development is constrained by limitations in the DoE methods available. Well, DoE is very widely used in the automotive industry, particularly in engine design, development and calibration, and I'll come on to what calibration is in a moment. It's a big area for DoE because there are lots of variables involved. They interact together, and a lot of responses are very non-linear, particularly where you're modelling engine emissions. If you like, the physics of emissions generation are exponential type functions, and they're very sensitive to small changes in pressure or temperature. Other reasons for using DoE is it allows you to assess the robustness of your system more effectively. So, as I said, DoE is widely used, and that's because it does reduce the development time, gives you better, more robust solutions, and it also gives you models that you can use to re-optimize your system if, for example, your objectives change. Okay, so DoE is used at every phase in engine development, from research, engine design, analysis, simulation, hardware development, calibration, and through into production. At the single cylinder, at the R&D stage, you often have a single cylinder engine, and that's, Okay, so this is a single cylinder engine. It looks a bit like a robot. The single cylinder engine allows you to put a lot of quite sophisticated instrumentation around the engine, and it may include optical access to the combustion chamber itself, and so there's lots of variables you can look at to do with the spray of fuel into the chamber and the air motion. So DoE is used at that stage, and at that stage you may have maybe 20, 30, 40 different variables that you're interested in examining the effect of. So DoE can help you navigate through that process. At the design and analysis stage, DoE is often used in conjunction with physical models of the gas dynamics or the mechanics of the engine in order to optimize the hardware of the engine prior to prototype parts being created. Once you have prototype hardware, it's then often the case that you will use DoE or a one factor at a time type approach, depending on the project, to test various candidate hardwares. And that's because current simulation models are not sufficiently accurate to allow you to get to the hardware first time. So you always have to test a range of different combustion chambers or camshafts or other hardware variables. And that process, as I say, sometimes uses DoE, but not always. Next we come on to calibration. The calibration basically means defining and optimizing the settings for all the variables that are controlled by the engine management system or electronic control unit. And this is a very big area for the use of DoE, and that's because you've got lots of variables. Testing is relatively expensive, but you've got lots of variables and it's difficult to deal with them without using DoE. So I would say probably 2/3 of automotive engine companies will use DoE for the engine calibration stage. Now some of these are steady state tests, so for a gasoline engine or a diesel engine, but there are also some applications where transient tests are conducted. For example, cold start and warm up, catalyst heating, transient fueling. Now often those transient models aren't really transient models, they're kind of metrics calculated from a transient event that you then model in a sort of traditional DoE type way. And then finally, important aspect is the robustness. You want low emissions in production, but you also want low variation of emissions because you have certain conformative production type tests to achieve. So DoE models combined with Monte Carlo simulation, for example, can allow you to predict the variation in emissions. So this would be the nominal engine emissions, and these are predictions of the spread of emissions for a population of engines through simulation. And from that we can see what percent of vehicles will be outside emissions limit. And then there's some other areas. Onboard diagnostics are sort of systems that monitor your emissions live as you're driving. And in production, sometimes DoE is used to resolve quality issues on the production line, or perhaps not as often as it should be. So a little more about engine calibration. So I say this is a big area for DoE. There's a conference in Berlin every other year, which is just on engine development using DoE. Always has a lot of a couple of hundred delegates from all over the industry, and it really is an area that I think statisticians and academia should get more involved in, because DoE in engine development is dominated by engineers, and what you really need is a combination of good mathematicians, statisticians and engineers to get good results. If you leave it to the statisticians, they'll waste time testing things that are never going to work. If you leave it to the engineers, they may not realise all the assumptions involved in the models that they're applying to the problem. So you need a good combination of skills and good tools as well. So the engine management system controls all the different variables on the engine, and there are literally tens or hundreds of thousands of individual parameters that need to be calibrated in the engine control unit. Obviously some of those are more important than others, but they basically say that if you're at this vehicle speed, with this in this gear, with this driver demand for a certain level of torque, how much fuel to put in, what the air system will be doing, any other emissions control devices. And that must work for all different speeds and loads, environmental conditions across the board. So The main variables, just to give you an idea of the physics, so there's air system type variables, which would be boost pressure, and EGR, which is used to control emissions. And on a petrol engine, you've got air system variables as well, variable valve timing, also have EGR in some petrol engines. And in the fuel system, in a diesel engine in particular, you may have up to 5 injections. And so in DoE terms, that's a lot of variables that you're dealing with, because you can determine the quantity and the timing of each of those injections. And on a gasoline engine, multiple injection is now fairly common on the type of engines currently being developed and going into production in the next few years. So typically between 4 and 10 variables to calibrate, which is kind of a nice number for applying DoE, and unfortunately the number of variables is increasing every year, and that will lead us on to one of the possible limitations in current methods that I'll talk about. Okay. So, a few more facts about engine calibration. Those 4 to 10 variables, depending on the engine, will need to be calibrated for every single speed and load that the engine will go through or operate at, and also for different temperatures or ambient conditions. So, although the number of variables might be 10, the effective number of variables that must be optimized or calibrated is several hundred, or can be several hundred. There's one big decision you make at the start of a calibration DoE, is that do you include engine speed and engine load as DoE variables, or do you do DOEs at lots of different fixed speeds and loads? So this is a key decision, and it kind of separates the industry between those who are using sort of advanced methods and those who are using more basic methods. So speed and load have a huge impact on emissions and fuel consumption, and they're also very non-linear in their in the response of emissions to changes in speed and load in particular. So that's one important fact. Another is that emissions in particular can be very, very non-linear and sensitive to small changes in engine operation, and that means that you have some issues with test-to-test repeatability, and if you like, the recent engine history, what tests it's been doing before, can affect the emissions in subsequent tests. So these are all things you have to take into account. Another point, testing is expensive overall, so it's maybe £10,000 a week to do engine testing, and you may have to do between 6 and 20 weeks of testing on a particular project. But because most testing is automated and runs through the night, if you like, the marginal cost of each extra test point is quite small. So, you know, changes in methods that reduce the amount of testing significantly are important, though improvements in the design that maybe save 5% of your test points is not so useful. And then finally, design space. Design space is often very non-linear. So this is an experiment with speed, torque, MAF, which is used to control EGR, boost pressure, fuel pressure, main timing, pilot timing, and pilot quantity. And you can see that the runnable range, the same MAF, can be very narrow depending on the speed and the torque, and possibly the setting of other variables too. So this means that, you know, trying to apply central composite designs or box banking type designs is not really appropriate for this type of application. Okay, so polynomial models. They dominate in engine DoE just like they dominate other areas of DoE, and it's always seemed strange to me because lots of times in engine testing we have characteristics which are either flat or improving slightly and then kick up into, well, if the engine goes into misfire or something. So you have this kind of shape here which naturally a polynomial is reluctant to fit. Now of course you can do various things with transformations and so on to improve the fit, but ultimately you're trying to force something that's got a predefined shape by its order and interactions to model something that doesn't really fit that shape. So say some companies, ourselves included, use the type of advanced models which are more flexible in terms of the shapes that they can model. Other disadvantages of polynomials, sorry if this starts to sound like a rant, but because of this inability to model things when they change by several orders of magnitude, it means you spend a lot of time pre-testing to get the ranges for your variables right, which is relatively slow, usually manual testing. Very sensitive to outliers. The handling of interactions is just simple, this factor times that factor, which is not really how interactions work in practice. Aliasing, not such a problem when you've got 4 or 5 variables, but once you're in the 8, 9, 10 type variables, you get lots of problems with aliasing, and you can get some quite strange predictions from polynomial models. Okay, skill required to get good results with polynomials, and they're not really suitable for global models because of the shape of speed and torque responses. Okay, so what are the alternatives? The main ones, radial basis functions, neural networks, and stochastic process models. And there are commercial tools available that will fit those types of models. They're much better for nonlinear responses than polynomials. It doesn't matter if your ranges are, well, it's easier to choose the ranges of variables because you can have wider ranges without it impacting model quality, and you can handle difficult variables, speed and load. Also multiple injections can also produce some quite nonlinear effects. Disadvantages, especially in the early days of them, was a bit of a tendency to overfit the data, because data for some responses can be very noisy, so that can be an issue, and often an expert user is required with those as well as with polynomial models. So I won't say too much about each of them. Neural networks, I'll just say a couple of advantages. They can be used with qualitative variables, so you could have a model that covers the transition between, say, 2 injections to 3 injections, which is difficult to do with other methods. They're also very fast in terms of the prediction time once you've created your model, which helps at the optimization stage. Main disadvantage, and I think most people find this, is the size of the data set required to train them can be very large. Radial basis functions, main advantage of these, I guess it's a non-stationary model, so you can have, which in theory could help with global models, because you've got different speeds and loads, you can have different characteristics in the model. Disadvantages, they do tend to be a little bit more sensitive to outliers than either neural networks or stochastic processes, the other method that I'll mention. Maybe also a point is that the main automotive DoE tool that uses radial basis functions its approach is to fit lots and lots of different types of radial basis function models, and then you choose the best one from those, so it can be a bit time consuming to fit those. Finally, stochastic process models. So these are based on Kriging and design and analysis of computer experiments, DACE. They work well with noisy data and generally more accurate than neural networks or radial basis functions with the sort of the small to medium sized data sets. This characteristic here, I'll just mention this because this is a real engine characteristic which for anyone who wants to argue about whether polynomial models are suitable for modelling all engine data, this sinusoidal characteristic is caused by pressure fluctuations in the fuel injection system. So it's a real repeatable physical phenomena. And this was on an early multiple injection system, and it's not such a big problem these days. But you want a modelling system where if that nonlinearity is there, you're able to model it. Okay. Main disadvantage with SPMs is computation time, and that's because once you've got your model and you come to optimise, as I say, you're optimising at all different speeds and loads over several test cycles, and you've got multiple objectives, multiple constraints, and a prediction function that's relatively slow is a bit of a hindrance. Okay, so that's just an example stochastic process model for, if you like, the main emissions for a diesel engine, which is fuel consumption, NOx emissions, and soot. The change in colour just means the model is extrapolating in those areas. And a 10 variable example like this will probably about 400 or 500 test points would be used to create that type of model. Okay. Where next? So this is kind of my opinion of where we would like some brilliant ideas from the academic community. At the design stage, range setting is the most time-consuming activity. You saw that very irregular design space. So some companies will use an online, on the test bed, automated method of trying to find the runnable region for the engine. And those online algorithms are quite slow because the data is a little bit noisy. So that's possibly an area where new methods could be developed. At the modelling stage, handling qualitative variables, that would enable a significant reduction in testing, because typically we would do tests, say with 3 injections and then another test with 2 injections, fuel injections. Computational overhead for SPMs is a significant issue, and then more generally helping engineers move away from polynomials to more accurate methods while retaining, if you like, the scrutiny and the analysis of the models to ensure that they're accurate. And then at the optimization stage, it's a large scale, sort of hundreds of variables, multi-objective, highly constrained optimization task, and if you like, the various different methods. There's genetic algorithms, gradient methods, but all of them are relatively slow. And maybe that's inevitable, but maybe there's better methods out there that can be applied to these types of problems. Okay, I'll try to give you an overview of the use of DoE in engine development and calibration. It's a heavy user of DoE, but many companies are using ancient methods like polynomial models, and there should be some scope for collaboration with universities for both basic and advanced users of DoE. Thank you very much for your attention. I'm happy to answer any questions you may have.
Okay, questions for Justin?
Hi, Michael Hopkins. Hi, Justin.
Hello.
It's a trip down memory lane for me, this, because I remember I was involved with Ricardo in the 1990s. In fact, I introduced the SPM methods there in about 1993. So it's nice to know you're still using them and they're still being effective. Quite a lot I'd like to ask, actually, but I think probably time is too short to discuss it. But one thing, I think you're right to concentrate on SPM methods. I think that's the way forward. However, don't necessarily discount polynomials, because in fact, if you take an infinite dimensional polynomial model and put a Bayesian prior over the terms, it's equivalent to an SPM model. It's another way of looking at it. So there are alternatives there for using different methods to achieve the same result. Question for you: when you're saying that you're reaching a computational overhead on prediction from the SPM models, what sort of order of number of test points are you using? How big are your predictors typically?
So the biggest, because SPMs are quite good with relatively small, medium-sized data sets, we wouldn't go over 500 test points in general. So if we've got 10 variables, including speed and load, we would have 500 test points.
That seems reasonable. For the computational time, you gave it n cubed for the predictions.
Yes.
Now, if you don't need the uncertainty for your predictor, you can get order of n. So that's going to save you an awful lot of time. It depends if you're using the uncertainty in the predictors as well.
So not during optimization, we don't.
Yep. So if that's one of
Is
your
it?
big...
Well, just subjectively, it does seem to go up more than linearly with number of test points.
Well, there are ways of the linear algebra lets you do that. If you form a construct from the model, from the modelling stage, you can then get the predictor's order n. But that's only if you don't want the uncertainty. I don't know if you're using the uncertainty within the prediction as well, whether you're just using the predictor without its standard error.
But during optimization, we don't compute the confidence interval.
You don't. Well, in that case, you can get a huge gain there by going to order of n for the predictors.
Okay.
Other things, I think optimal design for SPM models is a big benefit, especially as you go up to very large dimensions. You can get huge benefits in terms of the accuracy of the predictors by going to very good designs from the sort of standard designs, which typically are Latin hypercubes or number theoretic. And there are also methods that allow you to generate these designs within constrained design spaces very effectively, so that should be of great interest to you as well. There's a lot of stuff I'd like to talk about, the covariant structure you choose, everything else, but those are my main thoughts at the moment.
Okay, thank you.
Completely different sort of question, Justin, about training and engineers. But it mentions a name that Tim Davis also mentioned, which was Jim Morrison, who he's getting on a bit now, but he's been active as a statistician and through the engineering professional bodies. And that makes me wonder whether the engineers who are, those few who are aware of this sort of thing, are putting any pressure on the institutions, or could be persuaded to put some pressure on the engineering institutions to get this sort of thing taught to engineers when they're at universities, because we're not seeing much evidence of that.
No, the DoE is, I'm not aware of DoE being taught on any undergraduate engineering course, even though engineers are making decisions based on data.
Well, I teach 40 a course at Southampton that does
Latin
hypercubes and a few other things, but you can't go very far in the time that's that's available.
And in fact, I think there's often not even...
We need the pressure from somewhere else on the engineers to make the space in the syllabuses that will enable us to teach these very...
No, I totally agree, and I spoke to my old university about getting them to add some more statistics to the undergraduate course. I didn't get anywhere.
I think an impact of that is that when we're working with the engineers at GlaxoSmithKline, that they're unfamiliar with the concepts of DoE, and it takes an awful lot of discussion to actually get them to open up their minds to actually the possibility of that, because they've got these other techniques so embedded in
It'd be interesting to know, and I don't know the answer, whether other countries in Europe are the same as us, or whether they are better at teaching sort of statistical methods to engineers at university.
Just to add some texture to Dan's comment, I had a meeting at the Royal Academy of Engineering on Monday with a view to addressing this exact point. And so the purpose of me just intervening under the pretense of asking a question is to say that if anybody has views on how they can help formulate a joint approach with the Royal Academy and the other engineering institutions, I'd be happy to have a conversation today while I'm here and while the plans are just beginning to formulate. Incidentally, the meeting was prompted by Jim Morrison's article in the August RSS News.
Okay. Any other questions? All right, so let's thank Justin again.
Thank you.